Welcome, friends. We're gathered here today to get into the real antennas for the first time. And we're going to start with the monopole, the classic vertical radiator, modeled after the Brown-Lewis-Epstein work, supported by Krauss and Laporte in their own technical literature, and some from Terman. Now, I'm going to swap over to that vertical antenna on my Chalk and Talk. And here we have that vertical antenna placed over some form of ground. Yours may vary in its characteristics, but that's immaterial because we have a ground field underneath it, a radial system of we're not going to go into the number of radials, but we're going to presume that it's infinitely conducting surface of Earth. And this is somehow an approximation. The characteristic impedance of free space is 377 ohms, roughly. That's, let's see, I think that's, 377. Here we have the source, your transmitter, driving the vertical and the ground array. This is going to see a characteristic impedance, the whole system, including the antenna and the ground, as a plus and minus J, or inductor, capacitor. At resonance, these two are going to cancel, leaving us only with 37 ohms for a quarter wave radiator. So this is your classic monopole quarter wave tall, 37 ohm drive point impedance with a plus and minus J canceling. So it is in resonance. Anti-resonance would be a parallel circuit across that resistor. Right now, we're at the quarter wave. Now, this I represent as what would be called a fat radiator, a tower. A single wire will offer pretty much the same resistance, but the bandwidth is going to vary. This being a quarter wave tall, and being a thin wire, 37 ohms is perfectly suitable. We can have wider antennas that will change all of these at resonance. This will vary a little bit. These will vary widely. Not that they matter, because they will cancel. And we're going to look at those from the documents. Here we have a chart that gives us the radiation resistance in ohms for a vertical antenna. This is its radiation resistance up to, let's see, it's going to be upwards to 38 ohms at the top here. And the antenna height in degrees. So 90 degrees is a quarter wave, 90 out of 360 being a 1 to 4 relationship. And let's start with a very short antenna, let's say an 8th wave antenna, which is going to be 45 degrees tall. We can see that, 6 ohms of resistance. So if we return back to this has fallen from 37 ohms down to 6. Neither of those have, it's no longer resonant, of course, and there's going to be a huge amount of reactance involved here. So we've moved away from these balancing, and we've certainly depressed that number, 37. As the antenna grows taller, its radiation resistance rises accordingly. Now this doesn't go on to infinity, of course, but however, at the 180 degree mark, it's going to reach some very high value. We're off the chart up here, and we're off the chart in this direction. And this is going to create a very, very high impedance antenna. And that's entirely consistent with this series circuit turning into a tank circuit, a parallel circuit. So it's going to, where this combination of these two represented 0 ohms, the combination of those two in a parallel circuit is going to represent infinite ohms. So that's what's going on when we progress further to the right. This will rise to a very high value, typically several hundred, 600 ohms perhaps, because what's going on here is that the antenna is matching into this free space of 377 ohms, and you'll notice there's a 10-to-1 relationship here, even at this quarter wave level. Now, if you're tuning up your quarter wave monopole and you can measure it at something other than 37 ohms, there are antenna analyzers out there that will perform this measurement. It will also reveal these as well. If your monopole is something other than 37 ohms, look to the ground. And typically it'll be upwards to, say, if you have a good ground system, maybe 40 ohms. If you have a modest ground field, this might even be 50 ohms. If this were 75 ohms, well, that other resistance is coming from ground. So you're heating up ground. So returning to the literature, again, for very short antennas, very low radiation resistance, and this can be a point of disappointment and grief to someone who wants a very efficient antenna system. We'll return to that in more advanced fields. Looking at the reactant, looking at the resistance again, here's a mess of spaghetti that probably is going to confound you right from the start. However, it reveals what we're interested here is the antenna height over the antenna diameter. That's G over D. Now, G is in terms of the height of the antenna in degrees. So typically we're looking at a 90-degree antenna, the quarter wave right here, and its curve follows along here, where eventually it runs a very constant level irrespective of this ratio in this higher region. This means it's a very thin wire. This thin wire represents 37 ohms. Here's the 40 mark, 37 being slightly under. And it holds this consistently from a 1,000 to 1 height to diameter ratio to 100 to about 50, and then the resistance starts to rise to 50 ohms at a 20 to 1 height to diameter, up to something 55. So 50 to 55 in this region for ratios in this order. We're getting to very fat antennas now. This is saying that it's 1/10 as wide as it is tall. Over here it's 1/2 as wide as it is tall, and our 90-degree is probably tending down towards 1. Anyway, in this region, the resistance is starting to plummet. So, if we also look at this in terms of a very short antenna, a 40 degree, where it was formerly about several ohms, we note again 2 ohms for a very fat antenna to something over, slightly, right at 5 ohms at a 400 to 1 height to diameter ratio. So again, a thin antenna. But we get this variation. However, from this set of curves, we know, and this being the regime of most wire antennas, we can see that the height, the ratios and the height, or the tallness of the antenna, create various resistance readings upwards to, like I offered, 1 k ohm. And 160, yes, we're approaching a half wave at this point. Now, if we were to look at these same spaghetti nest of curves in the form of thickness and reactance, we get this very complex relationship. Here we have reactance ohms, there's the capacitive form, there's the inductive form. We see that as we're going from very fat antennas to very thin antennas, again, we're over in this regimen for thin antennas or wire antennas, or say a 1-inch radiator that's over a field of radials, 1 inch thick, that is. A very tall tube. Now, you might well ask, well, what's the purpose of all these curves, Richard? And why would I worry about thickness of my radiator? It's going to be some thickness, but that seems to be more an issue of physical necessity than electrical necessity. And that's very true. Let's return to the ham shack. Yes, this is all very true for physical necessities. We're certainly not going to have a antenna that is, say, 10 meters tall and 5 meters thick. That's a considerable construction. Economically, it's just off the charts. And, well, maybe it's not off the charts. Let's investigate what's the bounds. Now, before we investigate what's the bounds, what's the reason? Why would you want a fat radiator in proportion to its height? It's wider band. It can cover more of the band that you're working, rather than you having to tune. Now, a quarter wave that's a frequency. That's one frequency, and its bandwidth is for a typical radiator for your thin wire antennas. It's not going to be remarkably unsettling to your transmitter if you're off frequency of its natural frequency. It might require a little tuning, or you can possibly just work right into the swirl mismatch. It probably won't even rise above 3 to 1. I realize that some might step back from 3 to 1, but your transmitter's capable of doing that. If you don't want to do that, you tune. However, if you're in a contest situation, you don't want to be tuning. You don't want to be tuning your antenna or your system. You want to be tuning the rig, tuning it to a different frequency, say, and not having to do this as a three-hand operation. So that's why we go to thick radiators. But as I pointed out, that can be expensive. Expensive in terms of, metal, sheet metal if nothing else. So we're going to look at this from the literature again and approach this from a later topic, dipoles. But we're going to look at a dipole construction that reveals how to thicken your antenna. And moving on from this chart, here we have an illustration of constructions for cylindrical and biconical cage antennas. Now, the key word here is cage. And as you can see, these lines here that are running parallel to each other, or conical in this fashion here. Similarly, it's going out to the right. It's a mirrored representation that we're looking at here. A is the cylindrical form, and B is the conical form. Both yield a higher bandwidth antenna and a more stable, constant resistance and reactance, as you've seen from the other charts. Now, this says 6-wire cylindrical cage and a 6-wire cage for the biconical. 6 wires. Well, if this is a thick antenna and each of these wires is very thin, why do I call this a thick antenna? Well, luckily, through the cage, it's like a bird cage with a lot of wires going around. The cage presents a virtual, constant, uniform surface between those lines. And that's only if those lines are separated by a very, very small fraction of the wavelength that we're talking about. If we're talking about microwaves, those, no, this is entirely different. However, we're talking in terms of, well, when we return to this picture again, we're literally looking at a half wave from this point to the furthest point out here, or from this point to the furthest point out there. This is a quarter wave. The distance between these points is on the hundredths of a wave. And that's sufficient enough to create what would be a solid cylinder here and a solid cone here in respect to RF. And this can be observed through this graph. This graph gives us the relationship between the perfect cylinder. In other words, this line is for a continuous sheet of metal formed into a cylinder of a quarter wavelength long, which is to say, a solid sheet of metal surrounding a tube, presenting a tube, or presenting a cone here. So, this tells us how much capacitance we get from this surface for this radius of a cage. And you'll notice that we're getting out into significant sizes here. This goes out to 4 meters. It bears no relationship to frequency at this point. This is simply a capacitance, self-capacitance basically. It's what it's known as because there's no ground involved here. So this is the self-capacitance of a tube. This is the self-capacitance of 12 wires that travel parallel to each other along that axis, separated by one another by 30 degrees in this right here, this over this angle. And this goes what, 1, 2, 3, 4, 5, 6, so twice that. So this is pointing to a wire next to a wire next to a wire. Another wire would be here, a wire, wire, if we're looking axially down the length of the wire, or as a cross-section of the tube. And we'll notice for 12 wires that we get something less than 24 picofarads, that's microfarads, we get 20 picofarads. While the 6-wire one presents us with something about 16, we'll call it 16 picofarads, 16, 24. That's a fairly good approximation for a 4-meter cage. So we can easily build, well, if we had a 10 meter and it was a 1/10, that would only be a 10 meter tall antenna with a 1/10 wavelength thick radiator. The perfect radiator would or the perfect surface would present you with 15 picofarads, and the 6 would present you with about 7, something slightly less than half. So what we have here mimics the number of ground wires in earlier discussions from Brown, Lewis, and Epstein, in that there's a diminishing return for the number of wires that you keep adding to a ground field. In this case, the cage is quite well defined at 12. 24 would be probably in this region, and 48 and 96 and 100, and well, you get the idea. So these are the characteristics of the basic quarter wave antenna. Given its height, well, quarter wave is going to be 90 degrees tall, actually something less because of the end effect. But speaking generally, a quarter wave 90 degree tall antenna is presenting about 37 ohms of radiation resistance. And we call that radiation resistance because it's not lossy resistance in the terms of heat, but it is loss as far as the system is concerned because it can't recover that energy. It's gone into outer space. And hopefully it's working for you. The thickness helps us maintain tune over a wider portion of frequency shift. We'll go into the bandwidths of these systems later, but being broader typically helps difficult situations, and being thicker, again, okay, I think I mixed that up. Anyway, a thicker antenna is going to work over a broader frequency region. And a thicker antenna is going to present a more stable radiation resistance. And a thicker antenna is harder to construct if it's perfect. However, if you choose to go there, you can mimic it with a cage design, and there will be plenty of cage designs in the future discussions. So we're not going to orphan this concept right here. But I think that's probably enough, that's best said. So I'm going to offer my 73s. Hope to see you soon.